Hi, welcome to Real Learning Center. So we are going to basically go to the next topic on rotational motion. So we have seen that rotational motion has to do something with center of mass. Now what it has to do with moment of inertia. So let's see that part in the second session of the rotational motion. So let's see. First of all, if you say there is a mass and you have applying certain force on the mass. I have actually two masses. One is a bigger mass, another is a smaller mass. I'm going to push that with the same force, and you can clearly see the smaller mass gets accelerated more, in the sense that for the same force, lower the mass, higher the acceleration. This is nothing but our Newton's second law. So what is important here is that the shape of the object does not really matter. My first object was a little cubic, the second object was a little longer. So it doesn't matter actually. So irrespective of the shape of the matter, the force and mass are related in the same way as F is equal to m. Now let's understand this in the context of a rotational motion. So I'm going to basically have here again two masses. Both of them are actually of similar shape, but they are actually different mass. The first one is a bigger mass, second one is smaller mass. And I'm going to apply basically what we call torque. Torque is nothing but two forces acting like there are a couple of forces. I'm going to apply a couple of forces on both of them, and they are of the same quantity. The forces are not different for both. They are same quantity. What will happen? Let us see. You can clearly see the second one has picked up speed faster. So, which simply means that for the same couple of forces, lower the mass, higher the rotational acceleration. So this is same as Newton's second law. Okay, so there is no difference. Lower the mass, higher the rotational acceleration. So that we have seen. So similar. Okay. Only difference here is the shape of the object does matter. It matters. How does it matter? So let's see that how the shape of the object matters. Okay, let's say take this scenario. Okay, I'm going to have two masses which are exactly of the same mass, m. First one is thicker and smaller. Second one is thinner and longer. But they are all both same masses. And I'm applying the same couple of forces for them. Okay. And let's see what will happen. You can see that the second one actually is going slowly. Is picking up speed less, whereas the first one is rotating faster. So why so? Because for the same couple of forces and same masses, first one picks up speed faster. Why is it so? So this is because the moment of inertia of the is basically a new concept called moment of inertia, new entity. Okay, that is higher for the second mass, whereas that is lower for the first mass. It's like mass. Okay, but in this case, for rotational scenario, mass alone is not sufficient. We need mass and shape put together. We call a new entity called moment of inertia. So the moment of inertia is a combination of the mass and shape. So what is this moment of inertia? We can clearly see the second one is going slower than the first one. What is this moment of inertia? So if you actually see, mass resists translational motion. Okay, translational motion means moving from place to place. Mass actually resists that. Okay. That is called actually masses. That is why called as translational inertia. It's called translational inertia. A simple word is mass. Similarly, for rotation, you have rotational inertia. Okay. It's called moment of inertia. It resists rotational motion. If you try to rotate it, it resists that. Okay, that is basically called as moment of inertia. Now, if you take, for example, as an example, A and B, you see, A and B are both of the same mass, but moment of inertia of A is less than the moment of inertia of B. That means it is easier, less torque is required to rotate that, and the second one is little harder. That means it picks up slowly. Okay, so that is the effect of shape on the rotational inertia or a moment of inertia. Rotational inertia is same as moment of inertia. If you take these two masses for example, even here the A has lesser moment of inertia than B, though both of them being the exactly same mass. We can say it's harder to start the rotation of B than A. To start the rotation, it's a little harder to start the rotation of B than A. So similarly, you can see I have actually two, one disc, another ring. Both of them have the same mass, but moment of inertia is A is less than the moment of inertia of B, because in the B the mass is concentrated in the rim. Since the mass is concentrated on the rim, it is a little bit harder to rotate that. Not only harder, it's also a little bit harder to stop it, not just start it, because inertia is something which basically resists the change of state. That means if something is already moving with a certain rotational parameters, rotational velocity, it will continue to move. Then to stop that you need torque, opposite torque, and that torque is actually again harder to stop the one which has higher moment of inertia. So B is a little harder to stop. It's harder to start, harder to stop. So that is B and not A. So that is how the shapes actually affect moment of inertia, or moment of inertia, or what we call rotational inertia. So let's see basically, even in this, it's the same object. If you have a different axis of rotation, moment of inertia will be different. That means it is not only dependent on the shape and the mass, it is dependent on third entity called axis of rotation. So what is this axis of rotation? Let's take A and B. Okay, in A you have the axis of rotation is exactly at the center, in the middle. In the B, the axis of rotation is at the slightly at the edge. If you actually make them rotate, you can clearly see B is a little harder to rotate, picks up speed slowly. A is little faster. So that means that the IB is greater than IA. I is our moment of inertia symbol. When I say IB, moment of inertia with respect to the axis B. See, what is the axis? Axis here is a line that is basically perpendicular to the board, perpendicular to this one, and going like this. That is the axis. In both the cases, the axes are perpendicular, but in one case it is going through a center, in another case it is going through slightly off center. So in the off center scenario, moment of inertia is higher. In the center scenario, moment of inertia is lower. Okay. So even you can actually make it rotate in another axis. Look at this. I'm going to take the cylinder and put it in the circle on our side and make it rotate. So when it is rotating like this, the axis is like this. Now we will say the moment of inertia for that is IC. And since this is a little easier to rotate, so we'll say this is moment of inertia is even lower. So the lowest moment of inertia is the IC, and next one is IA, and next one is IB. So that is how moment of inertia is different for different axes. So we can say moment of inertia depends on three things now. Okay, it's rather mass, shape, size, and axis of rotation. Shape and size I am keeping it together. So basically mass, shape, and rotation, all of them are related to the moment of inertia. Okay. So this is basically a way of understanding moment of inertia. Now the question basically is, how is it related? Can we even calculate the value called moment of inertia? Like mass, easily we can calculate. Can we calculate moment of inertia? So it is possible. So let's calculate moment of inertia. How do we do that? Yeah. So we'll start with some definitions. Let us say first I am going to take two masses M1 and M2, okay, connected with by a massless rod, thin rod, massless. Okay. It's just a theoretical thing, very low mass. So M1 and M2 are connected, and let us say in the middle, that point is the center, and the R is the radius. So that means the distance, R is the distance between the center and the mass. Okay. What is that center? The center is nothing but, I'm going to put one axis like this, and that axis basically is the axis of rotation. So I will rotate it like this. So when you rotate m1 and m2 like that, the question that we are going to ask is, what is the moment of inertia? So the moment of inertia is given by a formula. It is defined like this. It is I is equal to m1 into r square, that is the distance to the mass, plus m2 into r square, that is the distance to that mass. And it happens to be both here same. Okay. Now, that is about the two masses. What if I have four masses, m1, m2, m3, and m4, and make them rotate? So then again, on the same axis, if they rotate, the moment of inertia is higher here. It's harder to rotate this. That will be actually equal to plus m3 into r square plus m4 into r square. So it is possible to basically construct such masses. That's why we can even construct, for example, more masses, m1, m2, m3, m4, m5, m6, m7, m8, several masses. And then say moment of inertia is nothing but add those masses also, m into r square, everywhere. So that is basically the moment of inertia of this whole system, and this will rotate like this. So when it rotates, this is the moment of inertia. That means this is basically the equivalent of rotational mass. Okay. Now, if suppose I want to basically write this as since r is common in this case, I can take it out and say I is equal to m1, m2, m3, m1 plus m2 plus m3 like that up to m8 into r square. You can write like that. Okay. Now, what I am going to do is I am going to replace these small masses, all of them are there, with actually a ring. A ring means actually if you get split into smaller masses. So many masses put together is that ring. So I'll call as basically moment of inertia of a ring. How do I calculate? Is I'll split into many masses, and that masses now I can say m1 plus m2 plus dot n number of masses, okay, into r square. R, all these m1, m2, m3, m4 all added together actually is simply the mass of the ring itself. That is what we call capital M. So if that is the case, then we can simply write I is equal to capital M into r square. So I is equal to mr square is nothing but the moment of inertia of this ring. You can clearly see moment of inertia here depends on the mass and also the radius. Higher the radius, higher will be the moment of inertia, and that would be especially on a square term. Even if you double the radius, moment of inertia increases by 4 times. That is how it is basically calculated of a ring. Now, the moment of inertia, we will say of a ring about, say this is how we specify, moment of inertia of a ring about the axis passing through the center and perpendicular to the plane of the axis, plane of the ring. So there is the plane of the ring is this plane itself, and the axis is perpendicular to this and passing. That is actually is equal to I is equal to mr square. So remember, some of these things needs to be remembered. Basically, they are very handy when calculating a few moment of inertia. Okay. Now, let's go to the official definition. Definition of moment of inertia. What is the definition? Definition is that you take any object, any random object, shaped object. We can actually cut that object into small pieces. Okay. Like this. You can cut them into small pieces. Any number of pieces, lots of pieces. And these pieces, let us say, when you cut them, and then assume that around this particular axis, we are going to rotate this. Okay. So if you rotate this around that axis, then we want to calculate the moment of inertia around that axis, about that axis. So what will we do? We take actually one mass, m1, okay, and basically find out the distance to that from the axis of rotation and call that as r1. You can take another mass, another piece of mass, say m2, and find out what is the distance from that and say r2. So you can take like that all n masses and calculate the distance r1, r2, r3, r4, r5, etc. Okay. And then you are going to use the same definition where moment of inertia simply is equal to m1 into r1 square plus m2 into r2 square plus m3 into r3 square plus m4 into r4 square plus dot up to mn into rm square. That if you add all of them for all pieces, you will get the moment of inertia of the whole of the object about that axis. Now, we can write it in a generic way as I is equal to sigma 1 to n mi square. So this sigma is a notation which simply says add for n terms. That's all. It's nothing more than that. Just add all the terms for n terms. For addition, there is a new notation. There's sigma mi square. So it is addition of many terms. This is how you can actually calculate the moment of inertia of any generic thing. Okay. Now we will actually do a little bit of some two theorems based on moment of inertia. So they are very handy theorems which will be useful for calculating moment of inertia of various different objects about various different axes. Okay. So now let us take one planar object. Okay. It has to be a planar object. That means an object has a very small thickness and a single plane. Okay. This kind of an object. And here you can actually write on the plane you can have x and y axes. They are perpendicular to each other, but they are on the plane. Now you can actually also have another axis called z axis, which is perpendicular to the plane. So there are three axes here. Now we can calculate moment of inertia about each one of these three axes. Like for example, we can actually extend this y axis here, and if you rotate it like this, then the Iy is the moment of inertia for that. So that's the name, I about y axis. Now similarly, it is possible to calculate moment of inertia about x axis, like you rotate it like this. Okay, I x. Then it is also possible to calculate moment of inertia about the z axis. I z about this axis and rotate like this. Okay. So there are three ways of rotation possible. One of them is perpendicular to the plane axis. The other two are on the plane, but they are perpendicular to each other. So the relationship between these three of Ix, Iy and Iz are given by the perpendicular axis here. And that relationship is Iz is equal to Ix plus Iy. So the one which is through the perpendicular to the plane will be actually equal to addition of the other two. The other two which are on the plane but perpendicular to each other. So if you add those two, you will get Iz. That is perpendicular axis theorem. So however, please understand this perpendicular axis theorem is applicable only for the planar figures. You can't take a huge cylinder and calculate, use the same theorem on that. Okay, this has to be a planar object. Then only this works. Okay. So there is a proof for that. So I'm not going into details of the proof, but this will be useful for solving some problems. Now, applying perpendicular axis theorem, I will tell you how to do it in a simple way. One simple question is this. See, if moment of inertia of a disk about an axis passing through the center and perpendicular to the plane of the disk is mr square by 2, if it happens to be mr square by 2, question is find the moment of inertia about an axis passing through one of the diameters, any diameter, one of the diameters. How do you calculate? So you use perpendicular axis theorem. You say you know that Iz has been given to you as mr square by 2. Okay, mr square by 2 is given as for this axis. Now, we know that by perpendicular axis theorem, Iz is equal to Ix plus Iy. Ix and Iy as two mutually perpendicular axes on the plane. Okay. Now, whenever they say that you calculate along the diameter, okay, it could be Ix or it could be Iy. Any one is along the diameter. And they have to be equal. But if you look at this very carefully, this is actually asymmetrical. Whichever diameter you take, you cannot have a different moment of inertia. There is a symmetry for that. Okay. So Ix has to be actually equal to Iy. To look at it. And hence, your Ix or Iy, if you want to calculate, will be equal to mr square by 4. Because one of them is mr square by 4, another is mr square by 4, added together is mr square by 2. That is Iz. That is how you can calculate moment of inertia in such scenarios. So there is one more theorem which we call parallel axis theorem, and this theorem is applicable to solid objects. Any solid object need not be planar. So I am just considering a cube, but it could be even irregular object. Okay. So now I am passing a line through the center of mass. There is a cm written in the middle, okay, center of mass. So through the center of mass there is a line passing through that, and around which, basically about which, I have calculated the moment of inertia. It's called as ICM. That is given. Now in such scenario, suppose if I want to calculate the moment of inertia, I put some other line. Okay, I have written another line which is actually a distance a from this axis. So what is important is that these two axes have to be parallel. So if you know the moment of inertia passing through the CM, which is parallel to your desired axis, then you can calculate the moment of inertia about the desired axis. Desired axis here is IA. On IA you can calculate about IA. Okay, so IA is about the axis that is passing through. So how do you calculate? There is a formula for that. That is what is parallel axis theorem. Parallel axis theorem simply states that IA is equal to ICM plus capital M into A square. That means you take the moment of inertia about the center of mass, okay, which is parallel to this axis, plus add to that the whole mass plus the distance from the center of mass axis. So center of mass axis is this, from there distance is A. That distance square you add, okay, MA square. If you do that, then you will be able to calculate the moment of inertia about that axis. Okay. And what is important here is this theorem is applicable to all objects. It need not be planar objects. Any object it is applicable. So now, if you actually see this theorem, how it can be used. Let us say I am having a rod. Okay, a rod. Rod's moment of inertia about an axis which is passing through the center of mass is given as ml square by 12. This is mass m and length L. Now, question that is asked is that you draw an axis which is parallel to this axis, but it is at the edge. And at that point of about that axis, can you calculate moment of inertia? So you can. If you want to rotate around that axis, you can calculate moment of inertia, and you can see that the distance that is called I edge. Let us name it as I edge. Okay, that is what. What is the distance? The distance is L by 2. So let us apply parallel axis theorem, which is nothing but I edge is equal to ICM plus M into L by 2 whole square. Now, if I want to calculate that, M is, we already know, ml square by 12, and this is ml square by 4. If you add those two, you actually get ml square by 3. And that is the moment. You can see that moment of inertia about the edge is much higher than about the center of mass. Always moment of inertia about the center of mass is the lowest. That means it is easier to rotate something about its center of mass. Anywhere else to rotate it is harder. Remember this. Anything when you want to rotate about its center of mass, it is the minimum moment of inertia. Everywhere else the moment of inertia is higher. So at the edge it is higher. So once we understand these many concepts, we will now be able to now do angular kinematics and angular momentum, torque, and all those things we can actually understand in the next session. Thank you.